So I'm Axel von Arnim from Fortiss. Fortiss is a research institute in Munich, a spin-off of the Technical University Munich. And I'm leading the development of the Neurorobotics platform. And this is Stefano Nardo. He's at Santa Anna Institute in Pisa. And we're both moderating the tutorial this afternoon and presenting to you the status update of the integration of the knowledge graph and the Neurorobotics platform, which I must say is the first step towards what was called before the joint platform and now EBRAINS, integrating the multiple HBP platforms together. And this effort that we're presenting now is a first conjunction of what is today SP5 and SP10, so the knowledge graph and the NRP, which will expand later to SP6 because the knowledge graph will be used to get brain models to work with the Neurorobotics platform. So I will first, in the first part, present in general the NRP from a very high-level point of view. You will have more technical details maybe in the next presentation from our colleagues presenting Spinnaker. And yeah, in the end, the prototype integration that we did so far and that we planned for HA2 with the knowledge graph. So why did we develop the Neurorobotics platform in HBP? It's, of course, to integrate both the physics world and the neural simulation world to give simulated brains a body, like was introduced in the very good presentation just before. So this slide would be a concept slide of how a neuroroboticist would combine physical simulation with a brain simulation. They would use a robotic simulator, like in this case it's Gazebo on the left, and they would use a brain simulator on the right. It's a screenshot from Nengo, and they would have to write a lot of middleware to synchronize both in real time and to exchange data using either ROS, YARP, or plain Python, or whatever. And this would be code a lot of code that would be very tailored to this specific experiment, and that would have to be adapted a lot from experiment to experiment. And that's why we provide the Neurorobotics platform, also called NRP. It's mostly, it is this middleware that we wrote for these users. So you see on the top left, again, the robotic simulator Gazebo. On the top right, the different brain simulators that we currently support. And in the middle, this yellow square is the main component of the NRP, which we call the closed loop engine. It is this middleware that synchronizes both and exchanges data. The little boxes called transfer functions are user code. The user still has to write some code, but it's kept super minimal, of course, because only the user knows the names of the sensor and actuators and the names of the population on the other side that should exchange data. We also provide a graphical interface. You see on the bottom, it's a web interface, which allows us to provide an online platform where you don't have anything to install, but also binary or source installable platforms where you run your graphical user interface from your browser. So this is just a screenshot of our website. You see all the different ways to install or use the platform. There's also a live USB image, but now we will stop maintaining it, so it will just stay with the last version from 6 months ago, because it's really a pain to maintain. But we have this binary installation using Docker that we mentioned before that takes really 5 minutes with a fast network connection to download it's all automated with a script. And the source install is a bit tricky, that's true, it was said before. But again, if you follow the steps of the documentation carefully is important here, you generally succeed in installing the platform from source. So that's a bit the server infrastructure. Colin was just there, and he's our partner in CSCS to support this infrastructure for our servers. So we are using more than 130 virtual machines and Docker containers in CSCS that are running permanently. the closed loop engine, so the server side of the NRP. There is one front-end server that is running the graphical user interface files for the user. It's enough for all the user, though for the back-end part, one virtual machine equals one simulation. It's because it's so heavy, because we're running in the background Gazebo, Nest in parallel, and all the middleware, and a ROS, which is huge, so that's how it works. Yeah, I would say later you will see that there's a project to make this more flexible. So now this little video shows how a user would typically create an experiment from scratch using whatever kind of installation of the NRP. They would just select an empty environment from a list of templates, give it a name, and start the platform with it. So there's no robot so far, it's just an environment. So this loads all the textures and is running Gazebo in the background. So you see you can already navigate in the scene, and from there you can add robots. So you can add multiple ones, the same or different robots. You can add a brain from the brain library. And this brain can be a Pine, Nengo, or Nest script. Then you can hack it as you want in the editor. You do have to map your populations with this graphical tool. This is because the NRP has to know about your populations to be able to connect them in your user code to connect them with the robot. So here we create, in this very simple 8-neuron brain, 3 populations, one for the sensor neurons, the actor neurons, and the record one is to just log spikes. And once you have the brain and the robot, the next step is to write your user code, your so-called transfer functions. You see the functions are very small, and these are your way to tell the system how to connect your brain to the robot, what to do with the spikes, how to translate this spike information into usable robot commands. So all you have to know here is at least the name of your sensors and actuators as ROS topics. And this actually you can inspect. We have a graphical tool that you can see the name of the sensors and actuators in the graphical user interface, so you don't have to hack too much to find this out. You have to know the names of your populations, but you know that because you define them yourself. And then you just write your code. In here it's a very simple code that is just making some linear transform from voltage values to commands for the wheels of this robot. Then there is a tool to add, to change the environment and add objects to the environment, objects which can be passive or active. In this case, this TV can be set different colors. It can also display images, so you can add textures to the TV or even simulate a movie playing if you have a vision application, for example. And then you can use different visualization tools like the brain visualizer. You see the neurons spikings in real time. So different colors are different populations. You see what the robot is seeing. So it just disappeared, but there's a view of the robot camera. And on the top, this is just a standard spike train. There's nothing special here. But there are a lot of monitoring tools for you to debug or observe your simulation in real time. So you see you can add multiple robots and so on. But I will cut here. So now I'd like to detail a bit more all the use cases that are possible with the NRP. And the keyword here is embodiment. So give a body to your neural networks models. And from the neuroscientist point of view, it's interesting to use a robot simulator, for example, to test their neural network with different embodiments. So the same neural network with different robots. This is this color detecting, color reacting Breitenberg brain that is implemented in a 4-wheeled robot, in a mouse model, or in an iCub model. And with this setup, you can just feed your brain model with different streams of stimuli. You know, instead of always feeding MNIST or for kind of very static data sets, the purpose of the NRP is really for you to feed with like real life data, even if it's simulated. So another nice use case is for visual applications. So we do provide quite some sensors in the NRP. Among them are the artificial retina on the left and the DVS cameras, also event-based cameras on the right, which can be very, very nice sources of stimuli for your brain models. So you see, for example, on the right, this is a bit bigger brain model with, I think, 5,000 neurons or something in different layers that is doing pattern recognition based on the flow of on the data flow of a DVS camera. So these are all applications from our partners that are using the platform. So also interesting for neuroscientists is to be able to use very different models, not only robots. So we have also a mouse animal model, so it's not robotic. And it actually has muscles. So the NRP provides muscle simulation using OpenSim, very widely used simple muscle simulator. And you see that the user here would command directly the muscles and not the joints, like in traditional rigid body robotics. And the muscles in turn are pulling or pushing on the joints. The other on the right is a compliant robot from University Ghent, Belgium. And so this has very interesting passive dynamics that are also very well implementable in the NRP. So what about if you have a very slow simulation, or if you want to post-process your simulation results? So we have two tools for this. On the top, this video shows that you can actually record a simulation. You might see this red button, round circle on the toolbar on the top. When you press it, it actually records all the events of the simulation. It doesn't record a movie. It really records the events as ROS-bags, for those who know ROS-bags. And it records the spikes, all the robot positions, the events like changing colors or whatever. And then you can replay it in real time. So let's say you have a super slow simulation, you let it run full night, recording it, and the next day you can replay it. So of course the events are being replayed, they're not recreated, but then you can use all the monitoring tools to monitor neural activity and so on, which is quite nice, or for a demo. And on the bottom, you see that you can also log data. So if you if you take from the examples the proper logging functions, which are a couple lines, and you add them to your simulation, you end up with CSV logs, like you see, that you can post-process in your Python scripts or whatever Excel sheet. And you will see that we will use this in the tutorial this afternoon. So this slide shows from the roboticist point of view, also nice use case with robot learning. So this is again this little Tigrillo four-legged robot from University Ghent, learning a new gait for walking. We do have a tool called the Virtual Coach. It's a scripting API for the NRP. So you can script everything in Python. You don't need to run the graphical user interface. And so you can just run batch simulations and run your simulations in cycle or in parallel on multiple servers. And this is very much appreciated for learning. So also interesting for robots for roboticists is to use a multiple robot setup, for example, to foster robot cooperation. So notably on the right, you see an interesting application from University Munich that are implementing a robotic arm collaboration to learn grasping, a bit like this famous Google experiment on hardware robotic arms that they had a couple of years ago, very much featured on YouTube. For simulations running in real time, interesting is to also to change the simulation while it's running. So for this, we have a couple of tools, not too much, I must admit, but you can at least change the lighting conditions. You can add whatever object to the simulation while it's running to add some perturbation. And you can also, you see on the right, you can drag the robot, so with your mouse, interactively. I think a bit later in the video, as I'm adapting the strength of the force applied to the robot, yeah, you will see that it's actually flying away. And on the bottom, you see that you can add noise to some sensors. So currently, we only support noise on cameras, but we have different kinds of noise, which might also be interesting to add perturbation to your simulation. So this is some ideas of what we want to do next until the end of SGA2. So we have a partner who is working on integrating the human, in the loop in two ways. So on the left, University of Weimar is developing an immersive systems with, it's a kind of heavy setup with special cameras that are taking super fast pictures on 6 different color planes. But it's quite impressive. It gets you into the simulation. It gets actually multiple people in the same simulation represented as avatars. And you can interact with the simulation itself through hardware actuators that are detected by cameras. And on the right, it's another approach from University Munich that is actually equipping you with visual sensors and projecting you into the simulation as an avatar. But as a physical avatar, not like in the other one as just a visual representation. So the physical avatar can interact directly with the robot. You can kick the robot with your feet, and you can take it. But this is work in progress, and you will see, I think, more interesting stuff at the end of SGA2 around this. And this is all videos taken from YouTube, not related to us, because it's so much starting that there's nothing to show yet. But we're working on integrating particle simulation in the platform so that we could simulate more interesting terrains like sandy terrains or even water. We have a PhD student at Fortiss who is working on robot swimming simulation, and in particular mouse swimming. And for this, we hope that particle physics will provide these kinds of materials in the platform. So, as was said before by Alberto, we are working also on distributing the NRP on the CSCS cluster. I won't detail too much, but this will happen probably beginning of SGA3. It's very long-standing and difficult works. There's a lot of issues with the clustering, but this might enable larger brains to run in real time on the platform. We're also working towards running different types of brains in parallel. A nest brain, Nengo, TensorFlow, whatever, in parallel on the same simulation, so kind of modular architecture. But this will happen at the very end of SGA2 as a prototype and will be fostered more in SGA3. And what is more interesting to us today is closing the loop with detailed brain simulation, SP6. So this slide shows symbolic representations of a detailed brain model that is, by the brain simulation platform, simplified into a point neural model that is usable from the platform through the knowledge graph. So here, that can be downloaded from the knowledge graph to the platform. Then you run your simulation, and the simulation produces log outputs in the form, for example, of CSV files that are uploaded back to the knowledge graph, which closes the loop so that SP6 users, brain simulation users, they can have a database of detailed brain models and their NRP simulations, running them, plus all the results of the simulation in one view in the database. So, and this is a bit what we will show you this afternoon in the tutorial. So now more details about this particular effort. I still have 5. So in HGA2, the purpose of this integration with the knowledge graph is to set up a prototype, so it will not be production ready. So we are adding categories called schemas in the knowledge graph to support the current format of the brains that we're using. So it's point neuron models in Pine or Nest. We're implementing, getting this brain models, these instances from the knowledge graph, downloading from a public URL into the running NRP simulations. Then you run your simulation in the Neurorobotics platform and upload the results into the knowledge graph with a graphical user interface. So there is nothing hacky to do here. But the result is just a link to a public location where your logs are actually residing. So this will be the goal for HGA2. Then in HGA3, we'll probably have a cleaner implementation. And an application still that we want to have also in HGA2 of this would be to run the SP6 cerebellum brain that was just presented before by Claudia in a simplified version of around 30,000 neurons. So get it from the knowledge graph, load it in the NRP. So unfortunately, it has a different format than the format that we use for our brain models, but we're currently implementing loading this Sonata format, how it's called. And providing a simple experiment, but there will not be in HGA2 a real use case with the cerebellum, just a simple use case for just showcasing the connection with the knowledge graph and provide back the simulation results to the knowledge graph. So that's a bit the idea. Okay, this architecture diagram looks very simple because it is very simple. On one side, you have the NRP with, as I said before, the front-end component, which is handling the graphical user interface. That is connecting through a REST API, so a web API, to the knowledge graph to get brain models, to get a list of brain models and display them in the list of brains that you can select from to add to your simulation. And when your simulation is done, the front-end part of the NRP is posting, so submitting your log results back to the knowledge graph. And to finish, this little video shows a bit how it looks like in the whole process from the user point of view. So here we are using a brainless CDP1 experiment, a mouse-based experiment, if you want so. So we're opening the brain editor. You see it's empty. It doesn't have brain loaded. So we're opening the brain library, and you see this orange box here. This is a remote brain, so from the knowledge graph. The blue ones, they are local templates. So we clicked on it. It has downloaded the brain script to the brain editor. And then you see that you can use all the usual tools from the NRP to monitor and visualize the neurons and their activation. This is now running. The mouse, you see it's activated here. And it's doing whatever it wants. But it's logging data as CSV files, which you can see on this bit fuzzy view that you can name your logs and submit them. You have to type them and submit them to the knowledge graph by just clicking the upload button. And then they are available in this view in the knowledge graph editor. Providing them in the search UI is a work in progress. We will show the concept this afternoon, but we're still working on it with the knowledge graph team with Oliver Schmidt. But you see with this example that the files are there, the log files have been pushed to the knowledge graph and, which is important, are attached to the simulation instance. So more on that this afternoon in the tutorials, where we will present you a live use case. And you will have the chance also to run this use case on our online servers. If everything goes well, we'll see after lunch. And this was me. Exactly 0.